Here we are going to look at connecting different combinations of resistors in both series and parallel networks. So if we look on the left of the screen here, we've got three resistors which are connected in series. We know they're in series because there is one path for the current through each of the three resistors. Now if we call the total potential difference here across these three resistors V volts, then the PD across resistor 1 we'll call V1, across resistor 2 V2, and across resistor 3 we'll call that a potential difference of V3. What we know is that when components are connected in series, the total volts are shared between the individual resistors. So what we can say here is that V will equal V1 plus V2 plus V3. So the total volts, V volts, are shared between these three resistors. In series, the PD across each resistor, when added together, will equal the total volts. But we also know that V equals IR, and so we can replace V here with IR. We can replace V1 with the current through the resistor R1 multiplied by the resistance R1. Equally, we can replace V2 with IR2, where R2 is the resistance of R2 and I is the current through R2. And obviously V3 we can replace with IR3. Now the current in each of these resistors will be the same. There's no junctions, no branching in this circuit, so whatever current passes through the first resistor must also pass through each of the next two resistors. And because the current in each resistor is the same, we can factorize this, cancel the current, and so the total resistance R will equal the sum of the resistances that are connected in series. If we'd got a fourth resistor R4 here, we'd have plus R4 on and so on. So when resistors are connected in series, in order to calculate the overall effective resistance of that circuit, all you need to do is add together the individual resistances. What about if we connect resistors in parallel? Well, if we connect them in parallel, the current here comes in and it arrives at a junction here, and it will split at that junction. Some current here will go up through this top branch, call that I1. Some current here through the middle branch, some current through this bottom one, and then when of course it arrives at this junction, those three currents will rejoin again. We'll have a current I here leaving this parallel network. Now what we know from one of our circuit laws is that the current going into a junction must equal the total current coming out of that junction. In other words, I here has got to equal I1 plus I2 plus I3. But we know, again, V equals IR, so I equals V over R. So here the total current I can replace with the total PD divided by the total resistance. The current I1 will be the PD across resistor 1 divided by the resistance R1. I2 we have V over R2. I3 we've got V over R3. Now again here we can see we've got V on both sides. If we divide through this equation by V, V's will cancel because the PD, when they're in parallel, the PD across each branch of the parallel network is the same and equals the total PD. So if I divide through by V, what will we end up with is 1 over R, 1 over R1, plus 1 over R2, plus 1 over R3. So there we have it. We've got formula for working out the effective resistance, effective circuit resistance when we have resistors connected in series, and also then here when we have them connected in parallel. Okay, well let's have a look at some problems involving resistors connected in series and parallel combinations. Here we have a circuit, we have a battery pack, negligible internal resistance. We'll look at internal resistance in a lesson later on. And we're asked to find, well, the effective resistance of this circuit. So the first thing we need to recognize here is that we have two resistors which are connected in parallel to one another. How do I know they're in parallel? Well, when the current leaves the power supply, it moves around here. As it gets to this junction here, it's going to split. Not all of the current that goes through this resistor, or not all of the current that comes from the power supply is going to go through this resistor. It's going to split at this junction. Some current will come this way, some current will come that way, and it rejoins then at that junction there. So it's in a parallel circuit. We've got different paths that the current may take through these resistors. We need the effective circuit resistance. So for parallel combination of resistors, we know that 1 over the effective resistance equals 1 over resistance R1 plus 1 over resistance R2. So 1 over R will have to equal 1 over 100 plus 1 over 250. And if you work that out, you will get 0.014. Now what we must remember there is that we've worked out not the resistance but 1 over the effective resistance of this combination. So now to get R, we've got to do 1 divided by this number, and that will give us 71 ohms. So basically we could replace these two parallel resistors with a single resistor of 71 ohms, and it would have the same effect in this circuit. So this is the effective resistance of this parallel combination. Notice that when we connect resistors in parallel, the effective resistance is actually less than either of the individual resistances, and that will always be the case. Part B then, that was part A. Part B, we know that V equals IR. I is the total current that flows in this circuit from the battery. We know that we've got a total voltage here, 6 volts, across a total resistance of 71 ohms, so we can work out the current. I equals V over R. We've got 6 volts in total across a total resistance, a total effective resistance of 71 ohms. And when you work that out, you will get 0.084 amps, or if you like, 84 milliamps. Okay, well, we have a second problem here. Determine the current in this circuit, the current I that's flowing from the battery. Now there's a couple of ways we could go about doing this. What we need to realize here is that I is the current that flows from the battery. That will be the current that flows through the 80 ohm resistor. Not all of that current, of course, will go through the 200 ohm or the 150 ohm resistor, because that current is going to split there at this junction and it will rejoin here at this junction. One way to do this would be to work out the total effective resistance of the circuit. So one of the first things we need to realize is that not all of that 9 volts will be across the 80 ohm resistor here, because the 80 ohm resistor is actually connected in series with this parallel network. So we've got 2 resistors here that are in parallel, but then this parallel network is in series with the 80 ohm resistor. Some of the 9 volts will be across the 80 ohm resistor, the rest of the 9 volts will be across the parallel network here. So what could we do? Well, we could work out first of all the resistance of the parallel network. So let's do that. So if we're going to work out the resistance of a parallel combination of resistors, we use the parallel formula. 1 over R equals 1 over R1 plus 1 over R2. We can work out 1 over R, and then we can work out R. Once again, don't forget, once you've got 1 over R, don't forget to work out 1 over that value to make sure you get the resistance then in ohms. So what I've found here is that this parallel network here, I'll circle it here, that parallel network there could be replaced with a single 85.7 ohm resistor. The effective resistance of this part of the circuit is 85.7 ohms. What is the total circuit resistance then? Well, don't forget, this parallel network is connected in series with the 80 ohm resistor. To work out the effective resistance of resistors in series, we just add them together. Remember the formula? They're in series, R equals R1 plus R2. And so we have a total circuit resistance here of 165.7 ohms. Here the total circuit voltage, the EMF of the battery, is 9 volts. So in total we've got 9 volts across a total resistance of 165.7 ohms. And what that means is we can work out the current from the battery. So I equals V over R. We can put in our values for the potential difference across the total circuit resistance and the value of that total circuit resistance, and we get 0.054 amps. I've rounded the answer here at the end to two significant figures because the data in the question here was to two significant figures. Or if we want, we could put that down as 54 milliamps. Notice here, although the current, we're working out the current in the 80 ohm resistance here, we can't just do 9 over 80, 9 volts over, because not all of that 9 volts is across that 80 ohm resistor here. That 9 volts is driving a current through the total circuit resistance, which is the 80 ohm plus the resistance of this parallel network. We've worked that out there. We've got 9 volts across 165.7 ohms in total, and that means the current that will flow from the battery is 0.054 amps. All of that 0.054 amps goes through the 80 ohm resistor. So if we needed to now, we could work out how many volts will be across the 80 ohm resistor. Because we could use V equals IR on that resistor, we could do 0.054 amps multiplied by 80 ohms, and we'd get the PD across that 80 ohm resistor. Equally, if we'd have done the effective resistance of this circuit, which would be 85.7, we'd multiplied that by 0.054, we would have got the PD across the parallel network. And don't forget, whatever PD is across the parallel network is also across each of these resistors. Resistors in parallel have got the same PD across them. But there we are. So this time we once again have a parallel circuit. We have a 15 volt battery, no internal resistance in this case. 250 milliamps flows from the battery. And we've got these, you can see, three resistors here, 1, 2, 3, in parallel with one another. Junction here, current splits, some current goes through the top resistor, some through the middle, some through the bottom resistor. We're asked to find the total circuit resistance. Well, how can we do that? We don't know the resistance of this bottom resistor. Well, we do know that 250 milliamps flows from the power supply, so we've got a total current of 250 milliamps. We've got a 15 volt battery here acting as our power supply, so we know that V equals IR. So if we use the total volts and the total current, we'll work out the total resistance. R equals V over I. In total, we have 15 volts across this circuit, and that 15 volts drives a total current. And what that means is the effective circuit resistance here is 60 ohms. So what we're saying here, that these three resistors in parallel, in total, their overall effective resistance when the three of them are in parallel is 60 ohms. Now, of course, we know that for parallel resistors, 1 over R equals 1 over R1 plus 1 over R2 plus 1 over R3, where R is the total effective resistance. So let's call that total resistance of the parallel network RT, the total resistance, and then this resistor here, the third one in the parallel network, we're calling R3. So calculate, hence find R, we're calling that R3 there now. So we know, we've already found that the total resistance of this circuit, and therefore the total resistance of the parallel network, is 60 ohms. We know R1. We know R2. We want to find R3. We can easily rearrange that formula. 1 over R3, 1 over 60 minus 1 over 220 minus 1 over 180. So there we have the value for 1 over R3. Don't forget then you've got to work out the resistance, 1 over that value. And to two significant figures, we will get 150 ohms. There we are, that's the resistance, well, what we've now called R3. The third resistor here in the parallel network is 150 ohms. 220, 180 and 150 ohms in parallel give a total effective resistance of 60 ohms. Okay then, again, we've got quite a complicated looking circuit here. So again, it's just worth taking a little bit of time here to understanding the problem before we try and start with any kind of calculation. If you want to pause the video and have a go yourself first of all, then go ahead. So what have we actually got here? Well, we've got obviously a 400 and a 200 ohm resistor here, which are in series with each other, but they are then in parallel with an 800 ohm resistor here. And then the whole of this parallel network is in series with a 200 ohm resistor. So what we'll have basically is a current that flows from the power supply. That current then will split at this point here, and some current will go through the 800 ohm resistor, the rest of the current will go through the 400 ohm and then the 200 ohm resistor. Currents from both branches will rejoin here, and all of the current then will flow through the 200 ohm resistor. So all of the current that flows from the power pack is going to have to pass through the 200 ohm resistor. Now what we're asked to do is to work out the reading on the voltmeter, determine the reading on the voltmeter. So we're going to need to know really two things. We're going to need to know the resistance. Well, we do know the resistance of the resistor, but we're also going to need to know what current passes through that resistor, so we can work out the PD across it using V equals IR. To do that then we need to know what current is passing through the top branch of this parallel network. To do that we're really going to need to know, well, first of all, what current flows from the power supply, what current goes through the bottom branch. We can then work out the current through the top branch. So the first thing really we're going to try and do here is to work out the actual current that flows in this circuit from the power supply. We know it's a 12 volt power supply. What we need to work out then is what is the overall resistance of this circuit. If we can work out the resistance of the circuit, we can work out what current must actually flow from the power pack. So how are we going to do that? Well, what we've got here in the top branch, we've got two resistors in series, so the effective resistance of that top branch is 600 ohms. That 600 ohm effective resistance then is in parallel here with this 800 ohm resistance. So what we can do then is work out the effective resistance of this parallel network using the formula for resistors in parallel. So here, first of all, there we are then. Using our parallel resistor formula, we can work out 1 over the parallel resistance as 1 over the resistance of the top branch plus 1 over the resistance of the bottom branch. Our top branch in total has got a resistance of 600 ohms. Bottom branch is 800 ohms. 1 over 600 plus 1 over 800, we can work that out. Don't forget that's giving you 1 over R. So we then work out the reciprocal of that, 1 over this number, to work out the resistance of our parallel network. I've just written down all these significant figures just so I don't get a rounding error later on. Okay, we'll round it at the end. So we can now work out the effective resistance of our circuit. So we have our 200 ohm series resistor, so we simply add that on. Resistors in series, we just add them together. We've got the effective resistance of the parallel network. This entire parallel network could be replaced with one 342.86 ohm resistor and it would have the same effect in the circuit. So the total circuit resistance now is 542.86 ohms. Now of course we can work out the current that flows from the power supply, then we can work out the current in the circuit. So that's straightforward enough. We know it's a 12 volt power supply. We know that the effective resistance of the circuit now is 542.86 ohms. So the current that will be drawn from that power supply is 0.022105 amps, 22 milliamps if you like. Again, we will just round it at the end. Now, once we've done that, of course, we can work out how many volts we've got across this parallel network, because we know that the resistance of that parallel network is 542.86 ohms, and we have a current of 0.022105 amps flowing into that. So here we go. There we go. 0.022105 amps. Resistance of the parallel network is 342.86 ohms, and therefore we have 7.5790 volts across the parallel network. The rest of the 12 volts will be across the 200 ohm resistor. Now of course, once we know the potential difference that's dropped across this parallel network, we know the number of volts that's across the top branch and we know the number of volts that's across the bottom branch, because they'll both get 7.5790 volts if they're in parallel. That being the case, we can now work out what current will flow through the 800 ohm if we know the PD across it. So here we go. So 7.5790 volts across the 800 ohm resistor divided by 800 ohms means we've got a current of 9.4737 times 10 to the minus 3 amps through that resistor. So basically here we've got a current of 22.1 milliamps coming through here. We've got 9.5 milliamps basically coming through this bottom branch. So the current that must flow through the top branch is going to be the difference here. So it's going to be 22.1 minus 9.5, because we know the current that comes into this branch here must equal the total current coming out again. So this current plus this one through the top branch has to add up to 22.1 milliamps. So we can work out now the current in the top branch. There we are. Again, I've written the answer down to 5 significant figures just because I'm going to round in the final step to avoid a rounding error. So we now know the current that will pass through the top branch of our parallel network, and therefore we know the current in the 200 ohm resistor. We know obviously its resistance is 200 ohms, so now it's trivial to work out the potential difference across it. And there we are. The potential difference across the 200 ohm resistor is 2.53 volts, or really we've just been given the internal resistance to 2 significant figures, so probably here even 2 significant figures would be appropriate for our final answer. 2.5 volts. There we are. So none of the individual calculations particularly difficult. The tricky part here is understanding the circuit, understanding which circuit laws we need to apply at each stage, and finding a way through the problem. So it's just worth taking a moment at the start and just making sure we understand how these resistors are actually connected together.